Swayam Prabha. Digital India. Educated India.
Welcome back to our NPTEL course on Muffler Acoustics. So, this is again the combined lectures 4 and 5, and in this extended lecture what we will do is that we will consider a 3-dimensional analysis of circular cylindrical mufflers subject where the ports are located arbitrarily on the inlet or out, arbitrary on the either on the end faces or on the side surfaces. So, single inlet and single outlet system. So, and hopefully we will be also able to see some MATLAB simulations, and so what we will do is that we will we need to probably revisit the contents of the last presentation, you know. So basically what we had the Green's function coming in somewhere here, you know. This was the Green's function in the Cartesian system and subject to I am sorry, the point source representation of the port, and this was for the uniform piston model in both in Cartesian system. Now, the key thing for this lecture for a circular cylindrical chambers, circular cylindrical chamber is that we need to make some subtle changes. We need to make some important changes to the governing equation. So, basically what we have is your del square plus k naught square, where k naught is again your excitation wave number. So, here we have r, theta and z, p is this thing and t is of course is varying harmonically. So, this is your minus j omega rho naught q naught. Now, direct delta function definition will change, that is the key point. So, let us say the source is located at r naught. So, we have a a circular chamber and r, this is your distance theta, and let us say this is z. Okay. So, for theta you have the h factor. So, here you have h r, h theta and h z. So, what are h r, h theta and h z? They are basically your scale factors. So, let us I think we did something regarding the scale factors a long time back in week 2. So, so this is given by the following thing. For the 2D system, z will obviously not be there, because mind you this is x is equal to r cos theta, y is equal to r sin theta. So, here you have r, theta, x and y. Okay. So, once we substitute this guy, we will see that this is sin square theta plus cos square theta root over this is 1, and h theta is so this will be your r square you can take this thing common, and this will become the same thing, s square plus c square, so it will become r. So, h theta is equal to r, h r is equal to 1 and h z is also 1. And what is del square? That is a Laplacian in the circular polar coordinate, circular cylindrical coordinates, and that is basically del square by del r square plus 1 by r into del r of r plus 1 by r square of del theta square and del z square. So, you get this Laplacian form. Okay. So, with these substitutions, all this thing, if we substitute back in this equation, what will it look like? So, it will look like we basically substitute in place of h r h theta z the equations, I mean the expressions that we have derived here, and that is your minus j omega rho naught q naught r naught r. So, these are your direct delta functions in cylindrical polar coordinates. Remember one thing, there is a small digression that I would like to make here, is that here r minus r naught into theta minus theta naught in the direct delta system, over when you do dV over this cylindrical volume, what does it mean? So, dV is r. So, instead of dV you write r dr, r d theta, that is your that is your small arc here, and so if you consider basically an elemental volume in the cylindrical polar coordinates, basically your d theta dr small this thing and something a top kind of a thing here. So, you get r dr d theta dz. Okay. So, r gets cancelled, and eventually what you will get is this is 1. So, basically the idea is that this representation is consistent with the definitions of direct delta function, and of course, I guess I forgot a term here, that is k naught square, I am sorry for that. So, k naught square is obviously there, the wave number. So, basically what we do is that we need to have, if you recall our discussions in the week 2 lecture, we need to find out, for simplicity let us say we set q naught to 0, and actually incidentally if you have a piston driven excitation. So, what we will do is that instead of this we will have u naught into f of f of r theta into delta z minus z naught. Okay. That will be there, provide if the port is located on the r theta on the on the end face somewhere here. If the port is located on the side surface somewhere here, then your this will become minus, then instead of this thing you will have your this thing say delta r minus r naught into f of L comma theta, where f of L comma theta is unity. It is basically unity over the port area, and it is 0 over all the side surface area where the port is not there. Okay. So, that is one thing. So, so we get basically this sort of a thing. Now, the key idea behind underlying this derivation now is to substitute the solution of a homogeneous equation, which I am going to write down now, is basically P r theta z. T I am not writing, it has understood e j omega t. So, this is a modal summation solution, which is nothing but this, subject to, if you consider a long circular cylindrical thing with rigid wall condition u or w is 0 here, u, or I would say u z is 0, u r is 0, and there is no, and u theta, mind you, u theta is, there is no condition on u theta. Okay. Only thing is that p of theta is equal to p of theta plus 2 pi. This will always be there. Okay. So, L is equal to 0, 1, 2 till infinity, and m is equal to 0, 1, 2, 3 till infinity, and n is obviously like this. Okay. So, this is your cos L pi z by L j m alpha m n r by r naught into let's say let's call this constant as C1. So, C1 L m cos m theta plus C2 L m sin m theta. Okay. So, this is the periodicity condition. As a result of that periodicity condition is very important. So, you will get the solution, you know, eventually when we do a variable separate form, this I think we discussed also some time back. You know, we have m as an integer value. So, m is the so this you know, the modes like this cos alpha m n r naught by r cos m theta or sin m theta, whatever you want to say. So, you can also write this as e j m theta, e j m theta and all that. So, basically these are called, you know, when for m is equal to 0, you know, we get something like a radial mode. You get basically radial mode, and when n is for m not equal to 0, m is equal to 1, 2, 3, whatever it is, then you get your you know, circumferential mode, but then in that case your n should be 0. So, m not equal to 0, say m is equal to 1 0 mode, 2 0 mode, 3 0 mode and so on. These are all your circumferential mode. As we saw, it will something like plus minus or plus minus plus minus. So, it is given in nicely in my book here. So, this is the book that has been published recently on the elliptical muffler design. We are not going to discuss elliptical cylindrical mufflers in this NPTEL course. This is an advanced course, but what I did was that I presented the solution of a circular cylindrical case as a degenerate case of elliptical mufflers, and what I can do is that I can show you the mode shapes of how these things would look like. So, just bear with me for a minute and we can have a look at the PDF file as well. So, you see these are the radial mode shapes of a circular chamber. We can also have a look at the PDF file sometime later, and these are your circumferential modes in the first column. Okay. So, plus minus plus and alternating signs, and then you have your cross modes when m and n are both non-zero. Okay. So, it is all documented in my in the recently published book on elliptical muffler analysis, circular cylindrical case being a part of that. So, what we do is that this is of course your non-dimensional resonance frequencies value is also tabulated in this book, and this is subject to this thing, this is equal to 0 at r is equal to r naught. So, you basically have to solve this numerically. This is all Neumann functions. Okay. So, that is what we do. We basically do that, and now once we get the modal solution, which is now I think it's getting a bit untidy, or I'll just box it something like this. Okay. So, we get this sort of a thing. Now, we need to substitute this guy back in this equation. Okay. Once we do that, you know, once we substitute this particular thing inhomogeneous Helmholtz equation, where the inhomogeneity can be a point source or a piston source, and then invoke mode orthogonality. So, unlike circular function, there are certain things with Bessel functions. So, it is orthogonal with respect to the weighing function r. So, alpha m, well, let us say m n r naught into r and j m1 alpha m1 n1 r naught in dr, people tend to write this here. Okay. So, once you do that, it's orthogonal with respect to r over 0 to r naught. This is non-zero only if m is equal to m1, n is equal to n1, and this is equal to 0 for m not equal to I if either of this condition is not met or is met, I am sorry, then this is 0, and cos theta, the trigonometric function are orthogonal in the regular sense. And eventually what you do is that you multiply by r dr d theta and integrate over the volume, and then this take this particular term to be along with the Bessel function, this is with trigonometric function, this is with the also trigonometric function along the z direction, and then invoke mode orthogonality, get the modal coefficients which are given here, C1 lmn, C2 lmn. Okay. Once we get that, then back substitute to get the Green's function. So, what we will do is that we will look at the Green's function solution and also the piston driven solution just in a while. So, this is the book I was referring to. So, this is the book that was published a while back by me. It is a Springer paper. So, what I am going to do is that I am going to go to the second chapter where the solution of this the solution modal solution is given for the circular cylindrical case. So, these are all elliptical things which are more complicated. So, you see this equation 2.58 is the case where you have this modal summation I was talking about. Of course, here you have not really enforced the rigid wall condition along the z direction, but once you do that, what we can do is that we can go to the third chapter of this book where the Green's function solution is given, and this is what you get. This is the modal summation solution for the elliptical duct, but let us focus on the circular cylindrical duct, and once we put the modal summation back, we are going to get this as the Green's function solution. Okay. So, I guess you said you see this j m alpha mn r by r naught and these kind of things. So, these are j m is, like I said, these are Bessel functions, ordinary Bessel functions the first kind, and Neumann functions do not feature in the circular cylindrical case because the origin is obviously present, and the Neumann functions would blow up causing singularity at the origin. So, they are not included in the solution. However, in case of circular cylindrical pipe with a circular cylindrical chamber with a concentric rigid pipe, then the origin would not have been present, and in which case it is necessary to include the Neumann functions. Okay, but here in this case the Neumann functions are not quite there. Okay, so this is one of that. Now, basically what we get is this is the Green's function, response port, source port, and cos. Eventually, you will get things like cos m theta r into cos of m theta s, and your plus sine of m theta r into sine m theta s, which can be combined into one trigonometric form, which basically tells you that because of axisymmetry of the nature, axisymmetry of the problem, only the relative location, relative angular difference between the inlet and outlet ports are of importance, not their absolute thing, unlike a elliptical thing. Now, these are, like I was saying, your integral of the square of the product of particular set of mode shape functions. So, these are found by orthogonality. They are basically closed form expressions for that. For example, a closed form expression for the first integral, that is this one in equation 3.4, is given by 0.5 r naught, this thing, which can be found out from different mathematical handbooks, and other functions are sort of trivially you can find it out. And it is also given such a function in other paper that was published also some time back in Journal of Computational Acoustics for a circular cylindrical chamber. You have this kind of a thing. So, I guess we can have a look at the muffler configuration. So, this is a end inlet and end outlet flow reversal chamber. Forget about the pipe, we are not interested in the pipe just yet. Okay. So, we are interested only in the circular cylindrical without a concentric pipe. So, this is the more, well, a little more larger font size of this Green's function. They are essentially the same, they are the same, and using that you can find out the impedance matrix parameter, characterize that, and this is the roots, non-dimensional roots, which have been tabulated also in my monograph. For the first as much as first 10 roots, first 9 orders and 10 roots each, that has been tabulated. Let me just show you that quickly. So, first 9 orders including the m is equal to 0 order and first 9 roots. So, such things are also seen in engineering books. So, engineering maths textbooks or things like that, or maybe acoustics book, you can have a look at these tables, but for rigid wall condition, that is the duct satisfying the Neumann condition, these tables are there. Okay. Now, you get this Green's function solution and mode orthogonality, and now basically again you have to integrate the Green's function over the port area. So, if the ports are located both at the end faces, as we saw in the configuration just a while back, you just have to integrate the Green's function j m alpha m n r by r naught multiplied by cos m theta r dr d theta over the end port E k, and E I is the other one, and the other function, if there is end ports located on the end surfaces, then z value, this particular thing z r, that can be simply be 1 or minus 1 depending upon whether the ports are on the same surface or on the opposite surface. If there is an end inlet and end outlet configuration, we said simply z is equal to on the same face flow reversal chamber, then z is equal to 0, you can substitute and you get 1, and if it is one port is on one of the end face, the other port is on the other end face, you set 0 here and L here. So, it can be minus 1, you get your cos L pi, L based on the value of L, it can be 1 or minus 1. For L is equal to 0, you get 1, L is equal to 1, you get cos pi, L is equal to 2, you get cos 2 pi, and so on. So, you get 1 or minus 1 depending upon the value. Okay, in this case we get just 1, that is why this the z term is taken care of, and you have to integrate the Green's function over both the receiver port and the source port and divide by the port area of the inlet and outlet ports to get the average response, you get the impedance matrix parameters. And other thing that I just wanted to talk about is that all the very briefly solving, getting the impedance matrix parameters by solving this inhomogeneous system of equation subject to homogeneous boundary conditions, that is everywhere it is the same, or the boundary conditions, that is the same as solving a homogeneous Helmholtz equation subject to inhomogeneous boundary conditions. So, what do I mean? This would require a little bit of elaboration, more of a conceptual thing. Now, let us consider a circular cylindrical, we are looking at the, let us say, the side view, we have a concentric chamber, something like this, okay, and we have a port like this. So, what it means that over this domain you still have this thing P is equal to 0, okay, and then you can express this as modal summation m is equal to 0 to infinity 1 to n is equal to 0 1 2 3 infinity C m n j m alpha m n by r naught into r, okay, and cos of m theta plus e to the power minus j k z m n into z, this entire thing plus you can call this C 2 m n okay, you get this sort of a thing. Okay. The solution of this is a solution of this equation, there is no source term here, but what happens really, over the annular surface where I have shown with the red hashed surface, velocity u z is 0 and u naught, let us assume you are assuming a uniform piston driven model here. So, it is u naught. So, u naught is equal to u z, which is non-zero. Okay. So, and in this port, immediately from the port chamber interface you can assume planar wave. So, u naught is u port, and in the port area you are assuming u naught velocity, u naught into e j omega t, that is a given, and that is equal to the velocity, particle velocity along the axial direction in the chamber, and the axial velocity in the chamber is 0 at the annular surface, that is at these points. Okay. And pressure, other condition of course is the pressure at the port is equal to the pressure in the chamber over the annular area. So, what we do is basically use these conditions to get this thing. So, how do we do that? For the axial particle velocity you have this condition u z t is equal to minus dou x of dou z. So, from this expression we can find out this term, and this is nothing but rho naught j omega u z. Okay. You can find out u z in terms of these things. So, u z is this entire modal summation is set to 0 here, and it is u p u naught here, and then again multiply throughout by j m alpha m n r naught by r, I am sorry, r naught by r is alpha m n into cos of m 1 theta, and integrate over the r dr d theta, and due to orthogonality of the modes only that mode will survive where m 1 is equal to m and n 1 is equal to n 1, and only the cos term will survive. Similarly, we need to multiply by sine, and then we will get the C 2 coefficient. Okay. C 2 m n and C 1 m n, like this we can evaluate, back substitute and get the final modal summation solution in the cylindrical duct, assuming a planar piston excitation. That is to say, there is no coupling between this chamber and here. So, this is a homogeneous equation subject to inhomogeneous boundary condition. Inhomogeneous VCs. Why? Because it's u z is 0 over the annular part, and this is equal to this over this part, and so basically we get this sort of a thing, and once we get that, we will basically get the solution. Impedance matrix parameters can also be obtained like this. So, now basically after that we can evaluate the transmission loss of such a system. So, what we are going to do now is that I can just show you some probably run some codes in MATLAB and talk to you about how the transmission loss is evaluated and all the integrals over these ports are done. So, actually before I do that, let me also just show you the how does it look. So, for the end port for the these are the integral formulations for the end port, but I guess we can have a look at such formulations for this port just in a while. So, this is my thesis in which the integral expressions were presented. So, if the port is located on the end surface, and it is the distance between the center of the port and the center of the circular chamber is less than the radius, then this expression would apply, cos m theta or sin m theta. These integral values are derived carefully, or you can also write this as theta naught. I mean, you can redefine the limits and all that. If it is exactly equal to the radius, then these limits apply, and if it is more than r naught, then the other limits sort of apply. And for it is easy to see when you have m is equal to 0 and n is equal to 0, you get back the plane wave mode, and in which case this will just become 1, and r dr d theta, in such a case this will also be 1, and you will see it is easy to see that you will eventually get back pi d naught square by 4, and theta naught describes the angular location of the center of the end port with reference to the x axis as shown in the previous schematic. So, eventually for a plane wave case, that is for the lowest order mode, plane wave mode, you will get back pi d square by 4, which is important for the sake of self consistency. And for delta is equal to 0, these things, the theta and r directions will decouple, and you will get, that is for basically for the concentric case, and you get back your r this thing. So, that would basically mean that only axisymmetric modes will propagate, and non-axisymmetric modes will not propagate. So, it brings a lot of important important conclusions, that if you center the inlet port. So, let us get back to the presentation. If you have a circular chamber and you center your port somewhere here, only m is equal to 0, or the radial modes will propagate 0 1 0 0 0 2 and so on. If the port is not, suppose it is offset at certain distance here, then of course all the other modes like m is equal to 0, m 1 2 3 4 all will propagate, and based on the location of offset location of this port here, delta, you can actually suppress the propagation of the 0 1 mode if it is located at exactly 0.6276 times R naught. If delta is equal to this thing, then the 0 1 radial mode will not propagate, because you see it's a nodal circle is there, and if you center it, the integral will evaluate to 0. Like this, there are a lot of interesting rules, that a lot of interesting observations that has come out. All this is possible by analytical formulations, and finite elements we can obviously validate. So, that is what I am saying, is that the J m alpha m n R naught into R s, this is 0 if R s is 0, m not equal to 0, and this is not equal to 0 for R s is equal to, and for the 0th order Bessel function, that is the purely radial modes, this is not 0. So, basically there are a number of conclusions, corollaries that were made, that for Z matrix parameter due to a concentric end port as well as between two concentric end ports located on the opposite faces is independent of the azimuthal modes, and the Z matrix parameter or impedance matrix parameters between a concentric end port and an offset port is also independent of the azimuthal modes. So, and similarly there are expressions for deriving integral expressions when the port is located on the on the curvilinear surface, that is the curved surface. So, there are different cases. The general expression is this: for m is equal to 0 mode, it is like this, and m naught is equal to not equal to 0, you get this thing. So, what we can possibly do is that basically go to the MATLAB code now, and we can run a couple of simulations, just to show the expansion chamber or kind of a behavior, or short chamber behavior, end inlet side outlet, or side inlet and side port. So, those special cases we can see. We will just see that in a while. What we do now is basically for the first time in this course, we are doing the 3-dimension analysis of although of only reactive mufflers and circular cylindrical geometry. Rectangular I kind of avoided showing you the code because of time management thing, but for this thing I like to spend some time and show you how these codes were written. Some of you can try on your own system. So, as usual, we have transmission loss port, which is the main file which invokes the transmission loss port, where the final computation of transmission loss from the overall impedance matrix is computed using in the terms of scattering matrix parameters. So, number of parameters have to be computed first. Basically, the n, L, m n value, the mode shapes, integral of the square of the particular mode shapes of the chamber, and then the integrals for the particular port. So, let us consider what we are trying to study here is let us say we have a expansion chamber. Okay. This port can be located somewhere here, and circular thing. So, inlet and outlet. Okay. So, we have this sort of a thing. Now, this is delta distance, then this is concentric port, this is offset port. Now, based on the value of the offset distance, this is the length L, diameter d, and d naught, and this is all port diameters are assumed to be equal. So, let us say d is equal to 250 mm, L we can vary, but we can also vary d and port diameters, but we just have to compute some integral values before. So, this is 50 mm and so on. So, now we get all these things. Now, what is happening here is that delta, we just get back to the code. We are going to analyze this thing for different values of delta. So, let us get back to the code where we compute the mode shapes, pre-compute the mode shapes first, and this is the cut-on frequencies, beta non-dimension values I was referring to in my book. These are for large orders are considered, as many as first 10, 11 orders, I guess, including the m is equal to 0 order, and first 11 roots of such things. So, it is a square matrix where the thing is done, and these values are computed by numerically solving the derivative of the Bessel function going to 0, evaluated using some Newton Newton-Raphson's method or bisection method. I do not remember exactly, but some numerical method was used, and and this Simpson's 3/8 rule is used to do general numerical integration, numerical quadrature. And what I have done is basically there's two separate files where I have written first is to compute the integrals over the port surface area depending upon the location of the port. So, these are the radius of the port and the chamber, tolerance limit where how many iterations is required. This was found to be good enough, and different cases based on the plane wave mode we have this, and I will not bother going through each and every line of the code, but basically they are based on what is given in the PDF files that I showed you about my papers and thesis and all that. And then you have your mode shapes pre-computed, and they are kind of they are nothing but integrals of r, j, m square, dr and all that. So, this for the plane wave mode, this is for the this for the 0n mode or generally mn mode, and this is these were pre-computed using things that were run. And then what we need to do is that let us fix up some values. So, that is why we first compute this diameter is fixed, port diameter and chamber diameter are fixed, length L you can vary, but if you want to change d, capital D naught and small d naught, you just have to recompute these values again. So, basically what is happening here is that we compute these things and then enter the same value diameter in the impedance matrix, which computes the once you and then you load in these functions SP1, SP12 mode, all these things are loaded here, and then they are passed on to this function, impedance matrix function where the actual response functions are computed, I guess here. So, this is the characteristic impedance, and for the first 20 axial modes and first 11 routes, 11 modes were computed, those many modes were considered, and for convergence analysis, and these are the mode shapes value L into L.5 and all that, depending upon whether P is 0 or not, and these are the modal summation approach, and the response functions were computed, and Z21 value was given based on whether you have a flow reversal chamber or a expansion chamber. So, we can do both. Z21 is given here, is specified in the this parameter. So, Z21 L means location of the port 2 with respect to 1. So, if we change L, you get expansion chamber. So, let's run the case when the port is located at the offset, and this offset I am deliberately choosing at 0.6276 times R naught, and when I run the code, I have already done it. So, so we get basically your this kind of a graph. So, you get this is K naught R naught, the non-dimensional frequency. This is not hertz, by mistake I have written hertz. So, K naught R naught, do you see this expansion chamber kind of a behavior? This is an expansion chamber, dome and trough. So, this occurs at we can figure out certain things, this occurs at 1.3. So, you can work out how much based on the L, whatever this is. This will, in terms of K naught L, it will work out to be pi, 3.14, and this is just K naught R naught. So, because we have basically what is L? L is 300 and 125. So, 300 by 125. So, 2.4 if you multiply by 1.3 roughly, you are getting close to it, you are getting quite close. It always occurs at 2 pi, 2 pi, 3 pi, but this in terms of K naught L, in terms of K naught R, these are the values. But what is important is that you are look at this value, it is because of the offset nature, you are getting a peak. The azimuthal modes are if one of the port is centered, other port is at offset, that is why you are getting a peak, otherwise this would have failed right here, and you are getting another peak at this thing, these are the cross modes, and K naught R naught, and then 3.05, this is a peak because of the radial offset. Now, we can have some fun here, we can sort of close this guy and make some simple changes in the code here. So, this is something probably once you write your code, you can do that. Who knows, you might be asked this in the final exam to run some MATLAB codes based on that. So, instead of port 1 is a concentric one, and if I choose this sort of a thing, let us see what do we get. So, it will take about a minute or less than that, or probably little over a minute to get you the curve. So, this is what we are doing while the code is running. Let me just go to the presentation, and in this we are doing a concentric case. So, we are doing something like this sort of a thing. So, delta is 0 for both things. Okay. In other words, we have brought this delta to 0 here. So, let us get to the presentation, I am sorry, to MATLAB and see what is the progress. So, it is about 500 time steps or frequency steps that it has to do. So, we will be there in just a while. So, we will see, we will still see this expansion chamber kind of a behavior, domes and trough, but then the peaks, the sharp peaky nature would attenuation peaks, that will happen at a much later frequency, possibly at from k naught r naught is equal to 3.05 onwards. So, constant. So, you can have certain things, you can offset one of the port and you can offset one of the ports and this thing. So, basically compare this with the graph here. So, this concentric chamber thing kind of breaks down at k naught r naught is equal to 3.83, which is basically a first radial mode frequency, and but this particular thing continues to do well even beyond this. Dome and trough continues to do well for end centered a concentric inlet and a offset port which is located at the radial mode. Now, let us do something even more interesting. We will close this figure and go to MATLAB and say figure 1, hold on, and do something interesting. What is that? So, we will change it to blue color to show different plot, and now what we could do is that we can put this as a port, instead of concentric we could put this as port 2. And this is also port 2, okay, that is there, and if you put this also as port 2, so what exactly are we looking at? We are looking at configuration something like this. Okay, we are looking at this thing. Okay, let us run it and see what does it give. Basically the dome and trough behavior will come down even faster. That the transmission loss behavior will come down even faster. So, note that in all these things we have considered as many as, let us go to the impedance matrix file. Well, we have considered as many as first 10 orders, actually first 11 orders of Bessel function and first 11 roots. If we put this as 0, 0, 0, 0, 0, we will just get the plane wave mode. So, we can see what sort of a behavior does the plane wave mode also give us, just as a corollary, but we will probably do it for a reversal chamber. So, we are running short of time. So, what we will do is that we need to skip, or not all cases can be considered, can be covered. So, we will we'll let the simulation run. Perhaps next time we will do it for a shorter frequency range. Okay, well, we are nearly there. Well, it fails down even faster. So, at a much earlier frequency, at basically at what frequency does it fail? Or the dome trough pattern, there is a collapse of the dome trough pattern. At least dome trough pattern you can get only at isolated frequencies, you are getting problematic thing. The muffler was transparent. So, the good thing about dome trough pattern is that at least where you have the problematic frequency range. But when this fails down, you not only get a collapse, you get a lot of troughs, and attenuation is also completely annihilated. So, as low as 1 point, well, k naught L is equal to pi, or the first axial resonance, it kind of, after that the plane wave would fail, and you getting, why? Because for such a configuration that is shown here, all the modes will start propagating. So, higher order modes, 1 0 mode will also propagate, and that, so you basically get a when you had basically this configuration, ends some concentric inlet and offset port, at least the frequency range over which the dome trough pattern occurred, that was enhanced, and because the 1 0 mode, the suppression of that was suppressed because of the concentric nature. Similarly, 2 0 mode, 3 0, everything was suppressed. Now, similarly, when you have the port here, one of the ports at the center, this at the offset, so 0 1 was also suppressed, but you have both the ports at the 0 1 mode node. So, but in such a case, all the circumferential modes will start propagating. So, we will see that this kind of fails at K naught r is equal to 1.84. Yes, so my guess was right. So, it breaks down at the onset of the first circumferential mode, and then the story is over. It is no longer valid beyond K naught r naught is equal to 1.84. So, the outcomes of this thing, there are lots and lots of things parametric studies can reveal to you. So, a strong analytical background is very much desirable. Then you can do this 3D effects in a very nice elegant manner, although this piston driven approach is somewhat an approximation, but 1.84 is the frequency at which it fails, but in the other case it fails at much larger range. What is the point I am trying to make? I am trying to make a point that the location of the ports has a lot to do with the transmission loss behavior. So, that is very important. Okay. So, if you can at least you can have concentric inlet and outlet ports, it is still good. If you can have one port offset at a certain thing, it is even better, but do not have both the ports offset, although they are both at the radial nodes of the radial mode, but that is not sort of recommended. So, I will close off this figure and do show you something interesting, even more interesting for a short chamber. So, I will put this as the concentric port. Remember, port 1 was the concentric one, port 2 is this thing, with respect to this thing. And so, basically what is happening is that you have this situation. So, this is the port 1. So, Z11 is this thing, Z2 is this thing, and with regards to the Z21 parameter that you see. So, before we actually run the code, we can use the same code to analyze a reversal kind of a muffler configuration. So, let us say this port is concentric here, and this is something like this. So, inlet, outlet. Okay. So, inlet and outlet, and the length is L. So, what we need to do in the code is just put Z12 is equal to 0. Basically, this port, if you consider a coordinate system Z is equal to 0 here, with respect to the port 1, this is also located at the same value. So, basically, let us go to the MATLAB code and just put Z21 is equal to 0, which I have done. So, it is a flow reversal chamber, and port 1 is the concentric one, this is the offset one at a certain location, and Z21 is also the same, because this is the cross impedance matrix kind of a parameter which is evaluated somewhere here. This is the cross matrix parameter PC21. So, this will give you the Z21 parameter, and Z12 is the same as Z21. So, this is the critical part is SP21 with reference to the port 1, what is the location of the port 21. So, this is what it is, and then let us hit run. So, you will see a flow reversal kind of a behavior, a lot of parametric studies that you can do on your own. So, let us demonstrate the behavior for a long chamber muffler configuration. So, what we are going to do, it is going to take a minute or so, and we will also analyze the case where we have plane wave mode. So, just you put m is equal to 0, n is equal to 0, and we can see the deviation, what the end correction does, what we were discussing all this while. So, you just have to bear for a minute, and next what we can do is that we can analyze a short chamber expansion chamber or a reversal kind of a muffler, and we see even for short axial chambers things can be good. So, bear for a minute, and you will get the results soon. So, well, we get the transmission loss characteristics of a flow reversal chamber. So, you see this is a peaky behavior. You, instead of a dome trough thing, now you are seeing a attenuation peak and a trough thing, and there are multiple spikes. This always occurs at 1.84 peak, and this is occurring at the cross modes, of course, and then you are getting a peak at 3.05, and 3.84 I guess, no 3.57, 3.84 somewhere here I guess. So, anyways, what we will do is that we will say figure 1, hold on, because all the higher order modes, at least the first several modes were considered. Now, what we can do is that we can change it to black color, and in the impedance matrix file, how about we change it to 0 and 0, that is we are considering only the plane wave modes. You can put 100 here, not a problem, and this hopefully should be much faster. Well, you are there. So, plane wave does not take too long to validate because there are lesser number of modal terms. So, we get this. So, you see a small shift, that means, so based on 3D the peak was occurring at 0.709, 0.71 K naught R naught is equal to 0.71. So, that we can work out the frequency, and for just on the plane wave it is occurring at I guess 0.68 or something like that, 0.66. So, there is a difference. So, 0.05 R naught, that is the difference. So, 0.05 into 125 if you do, well, you need to work out how much it would evaluate in terms of hertz, but there is a good 20-30 hertz difference in the attenuation peak. For different configuration you can have different attenuation ranges, different shift, the variable shift in the peak frequency predicted by the plane wave and the 3D effects. Now, basically if you put Z naught is equal to instead of this thing, if we let us have a shorter chamber and let us see what the behavior would be like. Well, this is not quite correct because we have not considered the higher order mode terms, but what I am kind of, let us get back to the original thing, and what it means is that we are considering a much shorter chamber. So, one port is at the center, other is at delta, and delta is 0.6276 R naught. So, you will see just in a while a fantastic broadband attenuation even a short chamber can give you, provide that you can offset the inlet and outlet properly. So, this is what I presented in my book. So, I am going to show you the graph of such a configuration while it is doing its job. So, if you go back to the close of this guy, in my monograph I have talked about this configuration. Let it load, we should be nearly there, we should be getting a very broadband attenuation. Well, this is what we get, and compare it with the other configuration. So, although at low frequency attenuation, amount of attenuation is relatively low, but you are getting a broadband attenuation, and this is what I kind of got in my Springer monograph, which is basically your it is not loading somehow, I am not sure why, but well, anyhow the point is that even a short chamber can get you a broadband attenuation, and you are able to get as much as, if you continue to go beyond, it is going to fail at a much higher frequency, probably about K naught R naught is equal to 6.8 or 6.9, something like that. But so these reversal chambers, what is presented here, they are used a lot in your as an end chamber in a more 3-pass or multi-pass perforated muffler system, as we discussed in the previous weeks 8 to 10, we are discussing all those things. So, the point is that if you have a bigger system, something like, so if you have a system like this, the problem, one of the research problems that comes in my mind, and that is that's been there for some time, if you have a perforated tube, you can try this is the length here. What is the location of this inlet and outlet ports, or the ports of the end chamber? This is perforated fully or partially depending upon what you want, this got some thickness, this baffle plate, and this is the end chamber which facilitates the flow reversal. So, these are the configurations what I presented in my book, and you can alternatively have another configuration, something like this, single pass tube like this. The flow comes here, it has to negotiate this, you can have this as a partially perforated tube. So, what is basically your optimal configuration? Basically this guy we know, okay, this guy we know, but we have to design this guy and this guy. What are the optimal location of this port here, and so on. So, all this needs to be done, and so 3D analysis of such configurations can prove to be very handy, and that's what we did. So, other thing that we can also look into is that analysis of side inlet in a side outlet configuration, but this is something that you should probably try on your own. This is something similar what we saw for a rectangular chamber with a end inlet and a side inlet and a side outlet. So, let me just summarize the result, rather than doing the calculations again. If you have things like, if you have a port in here and one of the ports is say located here at L by 4, other port is at L by 2, but this is say on this thing and this is at 90 degrees, sort of not able to draw it. This is something like this and this is like this. So, the included angle between this is 90 degrees, then you would get a broadband attenuation. You have multiple peaks and you will get a broadband attenuation. First, second, third resonance troughs are basically eliminated, and with 90 degree you can also get rid of the 1-0 mode, but 2-0 mode you are going to have problems, that at that point the attenuation is going to fail. So, anyhow the point is that such codes can also be used for analyzing a side inlet and side outlet, or possibly an end inlet and a side outlet kind of chamber. Your ports can be arbitrarily placed, and these results are match pretty well with 3D analysis, 3D FEM analysis, where there is a proper coupling between the inlet and outlet ports, that because the entire thing is taken as a continuum. So, with this thing I will stop here, and what we are going, so this brings us to the end of week 11 lecture. We just had a glimpse of the 3D analysis, but what we could also do is that there are lots of geometries there. As a final note for this lecture, piston driven model can be used to analyze a lot of configurations, but for systems such as extended inlet and outlet systems, one necessarily has to consider modal coupling, at least between the annular cavity, that is that is between if you have a chamber like this, something like this, between this part and this part and this part, there is a fully coupled system, one must consider that. So, hopefully we will take up that in the next week, the first few lectures, and then touch upon the dissipative muffler theory, because it is a huge theory, it is hard to cover in 1 week. We will just have a glimpse of that, and then but as a final note in this lecture, I want to say that analytical solutions are possible for a lot of geometries in which Helmholtz equation is separable. There are a lot of coordinate systems, circular, cylindrical and rectangular, Cartesian system present only the simplest one. The other one is elliptical system, for which I have written the monograph in terms of Matthew functions, radial Matthew functions and angular Matthew functions. So, they can be used to analyze elliptical chamber mufflers, which are used a lot in practical applications. So, other than that, of course, there is a concentric circular chamber with a concentric pass tube and so on. Then there are hemispherical chambers which can also be analyzed using piston driven model and all that. So, there are lots of things, conical pipes, perhaps conical chambers, and then there are advanced mode matching techniques. So, all these can be used to analyze reactive mufflers quite well, but I will probably stop here, because the idea was to get you a glimpse of the 3D analysis, and we will basically meet in the next week, where we will discuss the extended inlet and outlet system using analytical approach. Let us see how much we can analyze that using MATLAB code based on the time and the the codes, how much it is giving us results. So, till that time I will stop here and I will see you in the next week. Thanks.